The biggest thing we need to understand with limits is that in order for a limit to exist, the value of the function must approach the same value from the right as it does from the left. So they got to be meeting together. When I look at this diagram, let's say I'm going to say the limit of this function as x approaches 2. You got to ask yourself, as x approaches 2 from the left and 2 from the right, does it approach the same value from both sides? And in this case, it does. And that limit's going to equal 4. So in order for the limit to exist, it has to approach the same value from both sides. And that's the biggest thing about a limit. The trick on the limit, though, is that it doesn't have to have a value at that point. It can have an open circle there and the limit still exists because it's approaching the same value from both sides. And we're going to see that as we look at some examples. But that's the biggest thing about a limit. It's got to approach the same value from both sides. Here we have 3 examples of a limit. As x is approaching a. From both sides, this one's defined and the limit would be L. That's okay. The second example, as x approaches a from both sides, we see an open circle. Will the limit still exist at that point? Yes, the limit is still L. The third case, we have an open circle. The limit is still L. As long as it's approaching the same value from both sides, the limit exists. So all 3 cases, there is a limit at A. Let me just show you a quick example where there wouldn't be. If you had something like this, and there was an A, then you'd say no limit. It doesn't exist. Because from the left, it's approaching a different value than from the right. It's split. So if it's split like that, there isn't a limit at A. That's a big thing there. Okay, we can talk about a one-sided limit as well as an overall limit. In this diagram right here, I could say, what's the limit as x approaches 2 from the left of g of x? This little negative up there, that means from the left. So I'm looking at 2. From the left, what does it appear that the limit would equal? 3. That's from the left. Then I can also ask you, what is the limit as x approaches 2 from the right? So from the right, as we approach 2, what does the limit approach? 1. Okay? These are called one-sided limits. One-sided limits, they don't have to be on both sides. But if I said, what's the limit as x goes to 2, then what would you say? Does not exist or no limit. And that's because the limit from the left does not equal the limit from the right. They have to be exactly the same in order for the limit to exist at a single point. They have to approach the same value from both sides. They don't. So limit does not exist at 2 for this function. Just to make sure we got this straight, does the limit exist at 5? Yes. It has no relevance that there's an open and a closed circle here. That just means it's still approaching the same from both sides. This limit would be about 2, it looks like, at 5. Doesn't matter that there's an open circle there. Doesn't matter that there's an error at that spot. It just matters that they're approaching the same value from both sides. Here they have the formal definition. This negative means from the left, and the positive means from the right. So that's a one-sided limit. And remember, if they don't put the plus or the minus there, you got to look from both sides. Both sides have to be the same in order for that limit to exist. Okay, so how do we find a limit? Well, there's a lot of different things that we've used in pre-calcs in the past, and I'm just going to list a couple of them right now. What's the first thing you always try to do with a limit before? How about direct substitution? When you get a limit problem, I just try plugging the number in. See if it works. The time that you can't use direct substitution is when you get a 0 in the denominator. Then you can't use that direct substitution. Another thing you'd use would be to factor. Factor and reduce, and then use direct substitution. Okay? What's another technique you've used? You look at the graph. And I'm going to link that with the table feature. So using your calculator, the graph and the table on the calculator. There's another technique that's a little bit more complicated, but it has, once in a while, it's something that you're going to have to do. It deals with the radical. This is where you have to rationalize the numerator. And then after you do that, you use direct substitution. So direct substitution is used quite a bit with limits. And this will come back, I think, pretty nicely for you because it was a pretty good unit in pre-calculus on limits that you've seen in the past. So this is just applying and figure out how to get the limit. And for the most part, it doesn't matter how you find the limit. It's just understanding what a limit is and how you would actually get to that point. So let's look at a couple examples here. Could I use direct substitution on this one? Yeah, just plug it in. Plug 3 in there. So 3 squared minus 2 times 3 plus 1. 9 minus 6 plus 1 is 4. There we go. That's a limit. That's the limit as x is approaching 3. That's all we would get. The next example, could I use direct substitution in this one? No, because I got a 0 in the bottom. This might be a good opportunity for us to look at the calculator. We take out the graphing calculator. We put in the function into our y equals. So in parentheses, we put in square root of x squared plus 9, and then minus the 3, and then we divide that all by x squared. In this case, when you look at, let's say you start looking at the table. If we're looking at the table, where do we want the table to start at? Look at the limit. Where is the limit approaching? 0. So we wanted actually to go or start at 0. I would just start it at 0. So make the table start at 0, and then make your increments really small, like 0.001. And then by doing that, you can just look at your table. You look from the left and from the right. Now, you got to get out of your mind that the error has nothing to do with the limit. Nothing at all. Doesn't mean the limit doesn't exist. You just look from the left and from the right. So from the left and from the right, do they appear to be approaching the same value? Yes. What's that value? 0.167, which is the same fraction as, I think, 1/6, right? I think. So we get that just by the calculator alone. And sometimes that's the way we're going to have to evaluate a limit, is with the calculator. Next one, again, it's something that we really can't use direct substitution on it. So we plug it into our calculator, do the same thing. We type in the sign of just x divided by x. Make sure you ended the parenthesis first. Make sure that you're in radians because it's a sine curve. Set your table up so it starts at 0 and goes up really small. And just look at your table from the left and from the right. There's an error at 0, but that doesn't mean anything. Does it approach the same value from both sides? And what's that value? 1. This is actually a property that we will try to want to have memorized. It comes up periodically in limits that we are in calculus in general that we want to be able to be aware of. The third one we have the sine of pi over theta. That one we got to be a little careful with because it's doing something with the angle and it's a periodic function. So this one just takes practice with. But if I start by typing it in and I look at the graph, this time I'll look at the graph a little bit more. So sometimes the graph can give you more meaning than the table. If I look at the graph, what do I see at the graph at 0? I see some crazy stuff. I see some oscillating at 0. So this is what we would say oscillates. And if we see oscillation occurring, then that's an indication that the limit doesn't exist because it's not approaching one single value. So we would end up finding out that it does not exist at 0. If you zoomed in, like on that portion right there, a little bit further, you would just realize that what would happen, and I didn't zoom in the right spot, but if you zoomed in the right spot, you would just see more oscillating that's actually occurring. And that's kind of the nature for these types of problems. So as you zoom in more and more, you think you're going to get closer and closer to the limit, but really it just gets more chaotic and doesn't really approach anything. So you got to watch out for periodic functions, sine or cosine, that do something else with the angle themselves. Generally, if the graph looks well behaved, as you examine, a limit will exist. Sometimes there won't be, though. Like this one here, you have 1 over x squared. You know you can't divide by 0, and because of that, there's a vertical asymptote at 0. If you put this in your calculator, you would get a graph something like this. Well, at 0, as x gets closer to 0, the functional value appears to go to where? Infinity. So it's going to positive infinity on both sides. A limit can't go to infinity. So if you have something like this happen, you just say it does not exist. Does not exist in that case. This next one, we'd use our table again on our calculator and just plug that in our calculator, look at the table, and if you do that, you should see about 0.6 as well for that one. Comes down and can do that type of thing here.